Hey there, everyone. So, today I would like to continue our discussion about nuclear physics, now focusing in our positron, which is basically the first antiparticle that we'll be dealing with now. So, in the previous lessons, we have discussed all the way from an understanding of the atom as our civilization thought as something that's indivisible and you cannot break down into tinier parts, to something that's a bit more realistic with positive particles and negative particles, right? The plum pudding model. In fact, the plum pudding was a positive blob with negative particles inside. And then, through our practical approaches and observations, we could then get to a model which is a bit more realistic, in which we have positive and neutral charges in the middle. Obviously, between this process, they had to notice that there is a neutron, because back then they didn't. But then we had something a bit more realistic, in which we have a planetary model. Electrons, they are fixed in some distance away from the nucleus, and the positive and neutral charges, they are in the nucleus. And this is a bit closer to the model that we have nowadays, and it's the model that gives us the most prediction, and that's the model that you're most used to in our high school lessons. Now, even though this particle was initially thought of in 1928, only in 1932 was it actually practically proven. So only in 1932 we had practical evidence of the existence of this particle. And the whole point is, how did we get to this understanding? So we used something called cloud chambers. And I believe I've explained that before, but cloud chambers are basically chambers with a supersaturated fluid. Usually it's alcohol. So what do I mean by supersaturated? It contains more water than it would like to. So when any particle, as tiny as it is, goes through this fluid, it will leave a track, because the water, which is supersaturated in the alcohol, will liquefy and will leave a trace where this particle just walked by. So this is basically how cloud chambers work. But how can we actually get those tiny particles to go through them so we can analyze them? And that's the whole point of our observations. So what humans did, they climbed mountains, they got into balloons with one purpose: to get closer to the top of our atmosphere. And why? Well, our universe is huge, and far away from us, at every moment there are stars being born, stars dying, and those energies, they reach us. So when we have, for example, a supernova, just like the picture here, this supernova, when it bursts, it emits high energy protons and atomic nuclei in every direction. It just ejects them because it's a very energetic explosion. And those particles, they will travel through space, since they go in all directions, and some of them will reach us. Well, when they reach us, what happens to us? Well, we have an atmosphere, and something quite interesting happens. As these cosmic rays get into our atmosphere, they start to react with the particles that we have. So, oxygen particles, hydrogen molecules, all of those particles that are here, all those atoms, they they may be hit by those cosmic rays. So those cosmic rays, they will, well, in a way, they will decay, they will lose energy, they will become less energetic rays, and they will then just release their energy. They will just, um, their energy will be just released and distributed throughout the atmosphere. So if we're here at sea level, which is roughly the lowest we can go, if we try to analyze those rays, we will only get the very low energetic ones, the least energetic ones, because they have lost most of their energy in this huge layer of atmosphere. So that's why scientists got into balloons to try and get more reliable, stronger evidences of those rays. And that's why in 1932, Anderson, a researcher, published some results which showed strong evidence of the positron, some evidence that he got from cloud chambers. So first, how does a cloud chamber work? Well, we already know that particles go through some um, liquid, right? Some supersaturated liquid. However, how why do they move? Why do they spiral? Well, it's just because we may apply some field. So we may apply some electromagnetic field. So if you remember our electricity chapter, when we have a field and some particle moving through it, so let's say that our field here is downwards and our particle is moving at a velocity v to the right here, so field b is downwards, velocity v to the right. Our force, if our particle, using the right hand rule, if our particle was positive, it would go inside of the board, right? So the force here, the electromagnetic force that a positive particle would feel, would be inside of the board. So what if I have a certain plate in which my field is all going down? So going all into the paper here. What would happen if the whole page here has a field like that and my particle is going to the right, a positive particle? What would be the force? Where would the force point towards? Well, if we use the right hand rule, since the field is going in, velocity is to the right, the force would be up. Now, as the force goes up, this particle will move like this. But when it reaches, let's say, this position here, let's say this is 90 degrees, 1/4 of a turn, the force now, since velocity is upwards, the force would be now into the circle. So the whole point here is that this particle would develop, as we have discussed before, a circular motion. And what are the things which influence this motion? Well, since force equals mass times acceleration, and we also know that this is magnetic force, right? Or could be electric force as well. We've got K, V, B, sine of theta, right? If it's 90 degrees, then it's 1. So take a look, K, V, B. So the charge and the mass. So the curvature of this motion will change according to the charge and the mass of your particle. And that's expected. Think about it. You've got a charge, some particle, going very quickly inside of a magnetic field. And again, let's assume that this field is all going inside. When this particle gets inside, it will be deflected. If it's positive, by the right hand rule, it will feel a force to the left here. So it would deflect in that way. If this charge is more massive, then it will change less. Its trajectory will change less. If it's less massive, it will change really quickly. Think of this as your inertia. The more mass you have, the less prone to changing your direction you are. Also, the more charge you have, the quicker you are to change. Because the more charge you have, the stronger the force you will feel. So if you feel a stronger force, that will result in you moving quicker, changing your direction quicker. Your acceleration will raise. So if your charge, let's say your charge is larger, you will have also a small curvature, and if your charge is less, you will have a larger curvature because there's not enough force to stop you. Now, what would happen if this particle was negative instead? Well, we know this. That's quite easy. It would be exactly the same thing, however, on the other direction. If it's less massive, it will twist really quick. If it's more massive, it will take longer to deflect. If it has more charge, it will deflect really quickly. If it has less charge, it will take longer. So let's go back to our cloud chamber picture. So if you look closely here, you've got all kinds of particles moving, and we will be looking at many of those cloud chamber pictures to understand those particles and even the creation, the pair creation, as we're gonna see in a few slides. But how did we in fact actually get the result for a positron? So let me show you the actual picture that they took back in 1932, and let's go through this together. Now if you observe this picture here, and yeah, it's a cloud chamber. Those thin lines that you see here, they are traces of a particle. Well, the first thing that we can observe is that this particle is going to the left, right? It's moving to the left. So if our field was going inside of this paper here, or of this picture, then this would mean that this particle is positive. Okay, just to recap, force, so velocity going up, right? Velocity going that way. Our field going inside would produce a force to the left, which is why it's turning to the left. Now we can see something here, some black thing, which is a lead plate, a very thick lead plate. So this particle is basically going through this lead plate and curving more to the left. Now you might ask, okay, why do we need a lead plate? Well, think of this. With this lead plate, I can know for sure if this particle is either going from here up or from here down. Why? Well, because as this particle travels and touches here, collides with this plate and goes through it, it loses energy. And that's why this curvature here, so if we were looking for, I don't know, the radius of this curvature, it's going to be much less than the radius before. So this means there was some loss in energy here, and this radius is less. Well, so we have a positive particle, right? It's going from bottom top, and by this curvature and by measuring this radius, what Anderson discovered is that this is just like an electron, but it's moving as if it has a positive charge. So it's just like an electron, but with a positive charge. Mass is the same, all other values are the same, but charge is opposite. This actually led into a Nobel of Physics in 1936. So Anderson got it. And this was actually a very interesting beginning for what was yet to come. So this shows a nice drawing that was made using some information from cloud chambers showing a pair creation. So let me guide you through this. So we have here some gamma particles, highly energetic particles coming from the left. And here they collide with an electron with a fairly low energetic electron. And what happens is that this is so much energy, this collision has so much energy associated with it, is that that electron is basically stolen. If it wasn't an atom, it was just bounced, shot off from it. It was just in the middle of the way, very unlucky to be at that position at that time. And so it was basically shot off from the atom or from the air, from whatever it was. And we can see here that the energy which was released by this gamma particle led to the creation of a pair of particles. So here again, if our field is going inside of the board here, and again, if this, let's analyze for example this velocity here at this instant, it looks like there's a force going that way, right? So this means that this particle is positive. Likewise, down below, we can see that, well, if we use the right-hand rule, we would expect a force to be outwards. So that means that this charge is negative. So basically here, this is an evidence that we have from cloud chambers about particle pair creation. How can we obtain particles from energy? Now, some things that I think are important to notice is that the gamma particles, they do not show up in the cloud chamber. Actually, if this was the actual picture, this would all be black. You wouldn't see any of that. And that is because cloud chambers, they will only show traces of particles that have charge. If there's no charge, then it will leave no traces. So the electron here, the positron, the electron, and the other electron here, they all have charge. So that's why we can see them. However, I've cheated when I showed you here our gamma particles, but we wouldn't see them in a cloud chamber. So I'm drawing them here for you before they hit the particle, so you can visualize what's actually happening. So we could actually calculate how much energy is needed to create a pair of electrons, right? A pair of positron and electron. So let's do this. We know that energy is mass times the speed of light squared. If we go to our physics booklet, we can find out that the mass of an electron is 9.11 times 10 to the negative 31 kilograms. Now, this is the mass of an electron, which is the same as the mass of a positron. Remember, they have the same mass, just opposite charges. So how much energy would be needed then? Well, I've got two particles, so I will need actually the 2 times the mass of an electron times speed of light squared. This is equal to 1.02 mega electron volts per c squared times c squared. This is the energy equivalent of the mass of two particles, 2 electrons, or 2 positrons, or 1 electron, 1 positron. And, well, simply enough here, we can cross those two out. So that's 1.02 mega electron volts. That's how much energy, you don't have to memorize this number, but that's how much energy you would need to produce that pair of particles. Now, in the next lessons, we will be discussing about muons, pions, kaons, neutrinos. Just keep in mind that not all particles will be studied by us. There are many, many particles, subatomic particles, that are never studied, not even in some graduate courses, because there are so many of them. So there are a bunch of them which are very, very important, and those are the ones that we're going to deal with, and those are the ones which are in your syllabus. But there's really no point in showing you things which do not have proper applications for the exams, which we're going to cover here. However, if you're interested, we can do some research together as well. There's a lot of new stuff coming every single day. Just a few years ago, we had to discover some practical evidence of new particles, for example, um, the Higgs boson. So there are always new stuff coming up, and it's very nice to see things, new things happening and studying them as well.